Hi, hello, and welcome to another fantastic day of Calculus 3. What we're going to do today is talk about Lagrange multipliers. So today's not going to be a very long day, and a lot of stuff that we're going to do today is not going to be very difficult, except for the algebra. And if you remember anything from Calc 1 and Calc 2, is that the calculus isn't the difficult part. The difficult part's the algebra, and so it's going to be kind of true here as we're talking about Lagrange multipliers. So again, in this section, we're going to present Lagrange method for maximizing or minimizing a general function subject to a constraint or side condition of the form g of xy equals k. So basically what we have here is we're going to be given a function, or in this function, we're going to have a surface. And in this surface, what we're going to do is we're going to put a constraint on the surface, and that is going to be, we're going to have another function, but this function is going to be defined by k, a constant, meaning that here we have a surface, and here we have a surface, and here what we're going to have is just a level curve at whatever the k value is. And so when we plot these on a contour map, so over here is what we have as the contour map. When we plot these, what's going to happen is that our g of x, our level curve, is going to intersect our surface. All right? And when we intersect our surface, what's going to happen is it's going to cross a bunch of these contour lines. All right? And what we're going to be able to find is that when our level curve crosses all of our contour lines, we're going to be finding maxes and mins. And so here you see that our function, all right, it's contour lines, and as our function goes in the x direction, that our function, the values are getting bigger. So right here we would have like a max using our constraint, and then down in these two intersections we'd actually have the min. And so all we're doing is we're using a level curve to find a maximum minimum only on our constraint. We kind of done this before when we were finding kind of absolute maximums when we gave it a constraint when we defined the domain for the x's and y's. And now how we're going to be able to find this is we're going to be able to find this by taking the intersection, so where the level curve bounces off our surface, which would be right there, all right, what's going to form is a tangent line. All right, and so they're going to have the same tangent line at that point of intersection. And if we know that things have the same tangent line, then they also have the same normal vector. And because they have the same normal vector, then we can say this. Now again, another way of saying the normal vector is just taking the gradient of f, because that's the partial of x and partial of y. So what we can say is that this happens when the gradient of our f function is equal to some scalar, and the scalar is going to be lambda times the gradient of g. So their normals are going to be equal. They're going to be equal to some scalar. So I'm meant to erase. They're going to be equal by some scalar. So they're going to be pointing in the same direction, but they could differ in length, so we have that scalar there. And so that's why we're able to say the gradient of f is equal to lambda the gradient of g, because lambda is going to be some scalar. And what we're going to really try to find is we're going to try to find this lambda so that we can determine, okay, what's the max, what's the min on our, given our constraint. And so the lambda is going to be called the Lagrange multiplier. All right, and basically this is just more of how, this is kind of like the method. I'm just going to go ahead and just do the method so you don't have to read this. And we're going to do that involving, our problem. Here we're going to find the relative maxes and mins of our function. So it's kind of off of, you really can't see the question, for example, 1. But what we're going to do is we're going to use Lagrange multipliers to find the critical values of the function subject to the given constraint. We're saying we're going to find the maximum and minimum values. A given f of x, y is equal to 3x plus y, and x squared plus y squared equals 10. All right, so let's go ahead, and we have our function f defined. Let's go ahead and define our g. So g, I just took that off because it's taking it at Desmos, and I don't really need to worry about that. All right, so what we have is we have a function f and we have a g. And so I'm going to go ahead and write my g of x. Now, I'm going to actually write the surface and not the level curve. So x squared plus 10, x squared plus y squared. If I wrote, equals 10, that's actually going to give me the level curve. Here, I just want the function because I want to find the gradient. So I'm going to find the gradient f and the gradient of g. So let's find the gradient of f. And again, it's going to be a vector taking the partial derivatives of x and then partial derivatives of y. So when we take the gradient vector here, it looks like we're going to get 3 for x. And when we take the gradient, or when we take the partial with respect to y for a gradient f, we're just going to get 1. And then we're going to do the gradient of g. Thing popping up, it can mess me up. Gradient of g, which is just going to be the vector 2x, partial derivative with respect to x, partial derivative with respect to y. Alright, and again, if you recall, to find our Lagrange multiplier, it's just going to be the gradient of f of x, y is equal to lambda, the gradient of g of x, y. And then we're going to go ahead and set those equal. So 3, 1, and a lambda 2x, 2y. Alright, now, because these are two vectors, in order for two vectors to be equal, what I can say is, oh, hey, then the components of these vectors have to be equal. So I'm going to set the components equal to one another. And so I'm going to go ahead and write, well, 3 is going to be equal to 2x lambda. I'll say 2 lambda x. And you don't have to. The only reason I'm saying that is because lambda is a scalar. And then I'm going to say 1 is equal to 2 lambda y. Alright, now I'm going to go ahead and solve for these. Alright, so when I do that, I'm going to go ahead and solve each of these for lambda. And so I'm going to get 3 over 2x is equal to lambda. And on the right, I'm going to get 1 over 2y is equal to lambda. Now, because lambda is equal to 3 over 2x and 1 over 2y, what I can do is I can go ahead and solve for either 2x and 2y in terms of one another by setting those two equal to each other. So I can say 3 over 2x is equal to 1 over 2y. Cross multiply, I'm going to get 6y is equal to 2x. And so then I can say x is equal to 3y. Divide both sides by 2. So here, solving for our lambda gives us 3y is equal to x. Now we're going to plug this into our constraint. All right, and our constraint was x squared plus y squared equals 10. So I'm going to go to x squared plus y squared equals 10. Let me change up a different color. So x squared plus y squared equals 10. I'm going to go ahead and plug in 3y equals x. So for x, I'm going to go ahead and say it's 3y. So 3y squared plus y squared equals 10. And so 3y squared is going to be 9y squared plus y squared. That's going to equal to 10. So 10y squared equals 10. Divide both sides by 10. Y squared gives me plus or minus, I'm sorry, not yet. Y gives me 1. So y is going to equal to plus or minus 1. Square root 1 plus or minus 1. So if y is equal to plus or minus 1, and over here we have 3y is equal to x, I can go ahead and substitute that in. So when y is So when y is 1, 3 times 1 is 3, so x is 3. When y is negative 1, we plug that in over here, and we're going to get negative 3 for x. Now, here we have our points, and what we want to do is we want to see, are these going to be maxes or mins? And so we're going to go ahead and plug them into our function. We're going to plug them into f of xy equals 3x plus y to see if these are actually, see what they are. Are they the max or are they the mins? And so, based off of this, I'm going to go ahead and plug it into my function. And when I do f of 3, 1, that's just going to give me 10. And when I do f of negative 3, negative 1, that's going to give me negative 10. And so here we have a max. I'll go ahead and write these out. A max at f of 3, 1 equals 10, and a min. The iPad people did not do a very good job fixing this because there are some parts of my iPad that I can't write on now, and so I am ticked. Notice that. Alright, and that's it. I'm finished with the first one.